Hello. The topic for the lesson is the singular value decomposition. So let's begin with a brief overview of the lesson. In an earlier lesson, we talked about symmetric matrices, and we said that they have an orthogonal diagonalization, which means that they are really very useful in practice. Now, let's look at the matrix A over here, and I'll tell you that it's not symmetric, but then you might say, oh, it's not even square. So this matrix is neither symmetric nor square. So we've got two issues over here. It's not square and it's not symmetric. And the question is, how then do we fix that problem and make a symmetric matrix out of A? And the trick is to define a matrix B, which is the transpose of A times A. And now you see that this new matrix is square and symmetric. And in fact, if we now go a step further and compute the eigenvalues of B, you see that in fact they are going to be non-negative. In this case, they are positive. Just one point you might notice that they look like perfect squares, 25 and 9. So really, we've kind of squared over here, and so we need to take a square root. But with just those few ideas in hand, we can then talk about the singular value decomposition of A. So this matrix B will have some eigenvalues being symmetric, and those eigenvalues can be used to compute the singular value decomposition of A. So that's the idea. Start with the matrix A. It doesn't have to be symmetric or square. Define the matrix B like I've done over here. Find the eigenvalues, take square roots, and that's the starting point for the singular value decomposition. Okay, so now let's do things a little more formally. So let's say you have an m by n matrix A. Then the singular values of A are the square roots of the eigenvalues of A transpose times A. And luckily we have a nice function called singular value list, which can be used to compute the non-zero singular values for a matrix. Now the question is, how do the singular values differ from eigenvalues? Well, if you have a non-zero singular value and V is the corresponding eigenvector of A transpose times A, then the sigma over here, the singular value, represents the stretching of that eigenvector by the matrix A. So these singular values are actually kind of stretching factors for the eigenvectors of A transpose times A. So that's the idea of singular values. Start with the matrix A, do a symmetrization of it, so to speak, take square roots of eigenvalues, and you get the singular values. So as an example, here is a matrix A again. We first work out singular values with the definition. Then we use the singular value list function, and we get back just the same answer. Let's compute the eigenvectors of A transpose times A and check that we actually have the right kind of stretching taking place. So it's the 5 and 3 over here are exactly the singular values. Okay, so now we go to the really important concept for the lesson, and that's the singular value decomposition. I should warn you, this is a very technical slide. I'll try and go slow, but you'll pick up the idea as we go on by and by. So let's say you have an m by n matrix A, and you have the positive singular values of A arranged in decreasing order. So we ignore the zero values, we just look at the positive ones over here. Then you form a diagonal matrix with those singular values. You may not have enough of them, so to speak. So the R over here may not be very large. And then what you do is you work out the orthonormal basis for the eigenvectors of A transpose times A. Once you've done that, then you work out another set U1 up to UR by normalizing the vectors AV1, AV2 up to AVR. Now, again, you may not have enough vectors over here, so then you extend that to an orthonormal base of Rm. So you got now a set of vectors U and a set of vectors V, and then the singular value decomposition of the matrix A is going to be U times sigma times V, where U is the matrix formed by the U vectors, V is the matrix formed by the V vectors, and sigma is a matrix with all the diagonal elements over here being given by the positive singular values. Now, fortunately, we have a very nice function called singular value decomposition. Will do that for you automatically, so you don't need to worry about doing all this yourself unless you really need to check something. Okay, so as an example, is the same matrix A. Let's compute the singular value decomposition, you see it's got three components. It's got a U component, a sigma component, and a V component. And sigma over here is just the matrix based on the singular values, 5 and 3. So here's a singular value list, 5 and 3. Now work out the matrix V, and this is based on the eigenvectors of A transpose time A. So here you are. Let's check that. And finally, the matrix U is based on the images of the eigenvector of A transpose A under A. So here's U over here. That's the transpose of V. And if you work out the ratios over here, then you see that you actually get back the vectors of U in the first two columns. And that's just a completion over here. So basically, your singular value decomposition got three components, U, sigma, and V. And sigma is the part that depends upon the singular values. But that's a lot more complicated than an eigenvalue decomposition. So question is, what happens if you have a symmetric matrix? So here is an example. This is a symmetric matrix. In fact, it's positive definite. And then what you can do is compute the singular value decomposition. And then the singular values are exactly the eigenvalues. And the matrix V is based on the eigenvectors. And the matrix U, in this case, turns out to be identical to the matrix V. So let's check that we actually have the normal relation for orthogonal decomposition. And there you are. So for symmetric matrices, you actually have the same answer as for the eigenvalue decomposition when you do a singular value decomposition. So that's usually abbreviated as SVD. So SVD stands for singular value decomposition. Okay, so now let's take a slightly larger example. After all, in practice, you want to compute SVDs for pretty large matrices. I'm just going to take one of moderate size. It's 10 by 10. Compute singular value decomposition. Check the elements on the diagonal of the matrix sigma, those singular values. Let's check that. Let's plot them. You see there's one very large value, and then there are lots of smaller ones over here. Now question is how to check the answers. What you do is you do A minus the required expression over here, U into sigma transpose V, and then you apply chop, which basically takes away all the small parts over here. Then you flatten the list out into a long list, and then you figure out what the union of that is, how many distinct elements there are, and you do get back 0, which says that the answer is correct. So you verified that for this rather large matrix, 10 by 10 matrix, you can actually compute the single value decomposition quite quickly and check the answer. Now, as an application, let's talk about the condition number of a matrix. So let's say you have an invertible matrix, invertible square matrix, and you work out the singular values and you arrange them in decreasing order of magnitude. Then the ratio of the largest one to the smallest one is called the condition number of A. And roughly speaking, that tells you what to expect when you do numerical computations, how stable they're going to be. So a large condition number might lead to issues for the matrix. So as an example, here is a 100 by 100 matrix. Compute a singular value list. It's pretty large, so I won't show it. Plot it. Once again, you got one large value, etc. And then you compute the ratio of the first element of the list to the last element. And you see the ratio is about 4600. So that's a pretty large condition number, but not extremely large. So the condition number roughly tells you what to expect when you do numerical computation, but that's a very separate area from this course. So in future, I do hope you'll study numerical linear algebra, which will teach you details of condition numbers. But as far as I'm concerned, this lesson is now done and we can summarize. So the point is that there is a set of singular values that are associated with any matrix. And these singular values can be used to define a singular value decomposition for the matrix. That's a very useful construction which is used all over linear algebra. And finally, these singular values can actually be used to define a condition number, for the matrix, which is very useful to determine what will happen when you try and compute with the matrix. So that's the end of the lesson. I'll stop over here. Thank you very much.